Hi, in this lecture we will continue the reactions of alkyl halides, nucleophilic substitutions and elimination reactions. This is part 3. So in the previous lecture we studied the effect of leaving group on the rate of SN2 reactions, and we say that good leaving groups they have higher, or they occur faster in an SN2 reactions with respect to bad or worse leaving groups. So the reaction is faster for the substrate having good leaving groups. Okay, then one more thing, as we say that before, alcohols or OH is a bad leaving group because when it leaves, it generates a hydroxide ion, and it's very basic. So for that reason it's one of the worst leaving groups. So the reactions are very slow with hydroxide leaving group. But if you have an alcohol, you can make alcohol with chemical reaction, or you can convert the OH to better leaving group. So when you have thionyl chloride SOCl2, you can convert OH into Cl. You can convert an alcohol into an alkyl halide or alkyl chloride by thionyl chloride SOCl2. You don't have to know the details of the reaction, or if you have an alcohol, you can react with PBr3, phosphorus tribromide, and you can get an alkyl bromide. From an alcohol we can get an alkyl bromide with phosphorus tribromide, or from an alcohol we can get an alkyl chloride with the help of thionyl chloride. So these are chlorine and bromine. They are better leaving groups than OH. Another way to make hydroxide a better leaving group, reacting with this reagent, which we call, this is para-toluenesulfonyl chloride, PTSCl. That's the abbreviation. But what is this? So when you react an alcohol with this substrate, what happens? We form this group of chemicals or molecules which we call tosylates. So R, this is the alkyl part, then the oxygen stays still, but we get this tosyl, or this part is called tosylate. This is a very good leaving group, this part. Let's invest some time here why this is a very good leaving group. If you go back to the previous slide, tosylate is 2 times more reactive as compared to iodide. So this is the best, one of the best leaving group ever known. So why tosylates, this leaving group, you can say X or L, is the best leaving group? Let's compare with iodine. I'm going to write 2 reactions. Again, let's keep the same reaction. We have here carbon and 3 hydrogen, and with iodine, and we have a nucleophile, let's say Nu, and I'm going to change the leaving group with the tosylate. What is a tosylate leaving group? O, and this part as this. There's a benzene ring, I'll draw this way, and a methyl, and nucleophile, let's say here. So what's going to happen? Nucleophile will attack electrophilic carbon, will kick out this leaving group as this one. I'm drawing very primitively, so just look at the leaving groups. So this is the leaving group. So in this case, what's going to happen? Again the same, nucleophile, but that's the leaving group. So O S, so I'm going to just O, and this is the benzene ring. I'm going to draw the lone pairs also. There is a negative charge on this oxygen. Here, 2 lone pairs, and here 2 lone pairs. Okay, so why this leaving group, why this anion is the most stable or the weakest base, and then even iodide, because we know that iodide is the best leaving group in 7A. This tosylate, I'm going to write it here one more time so you can see better. This is the leaving group. Okay, let's keep going. Okay, let's draw the lone pairs also on these oxygens, because this is a very stable anion. Why it's a very stable anion? If you look at here, we can write negative charge on this oxygen, or by resonance we can write the negative charge on this oxygen or on this oxygen. So basically we have 3 resonance form for this anion, and this negative charge is going to be delocalized over 3 oxygen, and this will make this anion unusually stable. So that's the reason why tosylate, this is called OTOS, tosylate anion is, or tosylate is the best leaving group. There are some also good leaving groups as tosylate, but we are just covering tosylate in this course. Okay, so the resonance effect basically making this anion the most stable or the weakest base. Okay, let's continue the characteristics of SN2 reaction. The last effect is the solvent effect. So as you know, every chemical reaction mostly occur in solvents, and solvents, they affect the rate of chemical reactions in a couple of ways. Okay, so let's look at in this chapter, in this part, rates of SN2 reactions are strongly affected by the solvent. And protic solvents, those that contain an OH or NH group, are generally the worst for an SN2 reactions. And polar aprotic solvents, which are polar but don't have an OH or NH group, are the best. So what does it mean? It means that let's write the reaction again, a generic reaction for SN2 reactions. We have a nucleophile, generally negatively charged, right? So we have a leaving group here. So what happens? Nucleophile approaching the substrate and substituting or replacing the leaving group, right? And we are getting this product plus the leaving group. Okay, since the nucleophile generally is negatively charged or very polar species, we know that because they have electron density, or they are Lewis bases, so they want to donate the electron pair. So when you use polar protic solvents like water is a polar protic solvent, or sometimes like amine containing solvents or alcohols, these are all protic solvents. Definition of a protic solvent is it's polar solvents that are capable of forming intermolecular hydrogen bonding with each other. So what's going to happen if you have a negatively charged nucleophile? Negatively charged nucleophiles will be surrounded or solvated by polar protic solvents, so they will be shielded. If they are shielded, they will not be able to approach to the substrate, and they will not be able to replace the leaving group because they are shielded, they are prevented. So they have to shed the solvent shell first, then they will be able to approach to the electrophilic carbon. For that reason, polar protic solvents slow down or retards SN2 reactions. So what kind of solvents are good for SN2 reactions? Polar but aprotic solvents. For example, here like there are a couple of them. Dimethyl sulfoxide. What is dimethyl sulfoxide? It's a sulfoxide having 2 methyl groups. You see, it's a polar It's a polar solvent, sulfur, oxygen, sulfur, carbon, polar, but it's aprotic. It doesn't have any electronegative element having hydrogen. So protic, it's not protic. Or dimethyl formamide. This is an amide with 2 methyl group. So this is DMF, dimethyl formamide. This is DMSO, dimethyl sulfoxide, or CH3CN. Generally people know it as acetonitrile, meaning that it's a nitrile CH3. There is carbon nitrogen triple bond. So it's a polar solvent. It's a very good solvent, but it's an aprotic polar solvent. HMPA, hexamethyl phosphoramide. This is also a very good aprotic solvent. Phosphoramide, it's this. There are 3 nitrogens, and each one has 2 methyl groups. So this is called hexamethyl. We have 6 methyl phosphoramide. So basically the best solvent is hexamethyl phosphoramide, and the worst solvent for SN2 reactions are protic solvents. Methanol is the worst one. Okay, this is I think enough for solvent effect. So let's solve a couple of questions with respect to these effects. Before going into like why protic solvents are polar protic solvents are bad, why aprotic polar solvents are good, we can analyze in a potential energy diagram. For example, this is for protic solvents, and this is for, let me use aprotic. Let's look at here. If you use a protic solvent that is solvating the anion, solvating the nucleophile, what's going to happen? Solvation is going to stabilize the negative charge on nucleophile. So what's going to make it? So the reactants will be more stable when you use a protic solvent. But when you use an aprotic solvent which does not shield or solvate the nucleophile, the reactants will have higher energy. So this is related to activation energy again. So in protic solvents, which is the black one, we have more activation energy. In aprotic solvent we have less activation energy. Protic solvent stabilizes the reactants, and that's the reason they increase the activation energy. Okay, let's look at this question. Order each of the following sets of compounds with respect to SN2 reactivity. Let's look at, we have here 3 substrate. This is a tertiary halide, this is primary halide, this is secondary halide. All have same leaving group, so substrate bulkiness or steric factors will be important. So this is the most reactive. Okay, so let's say this is 1, and this is second reactive, and this is going to be the least reactive or the slowest one. Tertiary is the slowest, primary is the fastest. Let's look at this one. Again, we have bromine, bromine, bromine leaving group. So let's look at, this is a secondary bromide, alkyl bromide. This is a primary bromide, and let's look at this one. This is again 1 carbon, right? This is primary. Okay, let's look at which one is going to be the fastest. Here, like a general guideline, which one is the most crowded? Here, if you look at secondary and primary, you remember a neopentyl. This is neopentyl bromide. Neopentyl bromide is like even less reactive. Even though it's primary, it's going to be less reactive than a secondary. If you go back to this order, let's go back here. The methyl fastest, then secondary, primary, secondary, and here this is the neopentyl. It's primary, but the second carbon has 3 methyl groups, which almost blocks this carbon for incoming nucleophiles. Okay, let's go back here. So which one is going to be the most reactive? So we have to say that this is primary, right, is going to be the most reactive. Let's write here. So this one is going to be number 1, this one is going to be number 2, and neopentyl will be number 3. This one is easy. I think this is the leaving group, right? Alkoxide OR. When it leaves, there is a bond between carbon and oxygen, right? So this is the leaving group. This is the anion. OTOS. This is the leaving group. Let's say the carbon oxygen bond will break. Carbon bromine. This is the bromine bond will break. So this is the leaving group. So let's compare. This is one of the one of the worst leaving groups, right? Highly basic. So it's going to be number 3. This is the best leaving group, number 1. Bromide is the second. Okay, in this slide you will see the summary of all effects. The first one is with respect to substrate, hindered substrate, unhindered substrate, or you remember methyl, primary, secondary, tertiary halides. Tertiary is the least reactive. Why? Because it's sterically hindered, right? The carbon, electrophilic carbon, so nucleophile cannot approach. What happens? We increases the energy of transition state when we have hindered substrate. So the energy of reactants are almost same, primary, secondary, tertiary, but when you have a tertiary substrate, it's sterically crowded, so it has higher activation energy. So this is related to destabilization of transition state. Second one, good nucleophile, bad nucleophile. Good nucleophiles are more basic species, right? When you are more basic, you are more reactive. When you are more reactive, you are less stable. And what's going to happen? We are increasing the energy of reactants with the good nucleophile. Transition states are almost the same, so we have less activation energy with good nucleophiles. The third one is the leaving group. As you remember, leaving groups, when they leave, they leave with a negative charge, right? So during the transition state or at the products, they have negative charges. Whoever can stabilize the negative charges will be more stable. So what does it mean? Whoever can stabilize the negative charge during the transition state. So what we are doing here, we can stabilize the transition state. Weak bases can stabilize the transition state. Why? Because they are weak base, they are not reactive. So weak bases are the ones that can stabilize the negative charge. Larger ions or ions with more resonance form, they are good leaving groups. So here it's related to also the transition state stability. The last one, solvent effect. As you remember, for SN2 reactions, we have in the rate determining step, in that single step, we have a negatively charged nucleophile. Polar protic solvent stabilizes by solvating or shielding the negatively charged nucleophiles, so they stabilizes the nucleophile, they lower the energy of reactants, so that increases the activation energy. But polar aprotic solvents, they don't shield or they don't solvate, so the reactants have more energy and they will have less activation energy. So this is related to as in B, the energy of reactants. So we finished SN2 reactions, and in the next lecture we are going to cover SN1 reactions. Thank you so much for watching the part 3 video.